It's a pleasure to be here in Agra after 20 years, and it's also a great honor for me to be here and learn about nanocomputing and soft computing and quantum computing and understand the difference, because I thought all of those things were somehow the same before I came here. But what I'm going to talk about today is kind of tangential, but it could be one of the holy grails in terms of realizing the full potential of the different paradigms of the novel computing techniques that has been discussed in the last couple of days. So in my group, basically what we do is we make nanoscale structures of various different materials. Could be semiconductors, could be metals, could be insulators. And we control the properties by placing atoms in configurations that we can control or we can direct. And we want to use these nanoscale building blocks. We want to use them as building blocks to make larger scale architectures. And those would be, of course, building blocks for devices in a chip. So in order to actually give you a perspective, from what I understand, most of the computing paradigms discussed here are used as simulation tools or modeling tools to model problems or solve computational problems. But what we do here in my group could give you perspectives on what are the real challenges to make devices that use these kinds of computational paradigms at the chip level itself. Before I say anything, I just want to acknowledge my students and postdocs who did the actual work that I'm going to present today. I don't have enough time to thank all of them, but I have students Saurabh Agrawal, Darshan Gandhi, Arup, Chingyu Yan, currently, and several others who are working around the world right now, and collaborators also who are from various different parts of the world. Arijit Bose, Moshe Eisenberg, Ivan Petrov, Kim Turner, Klaus Kern, and others. And I'm, of course, eternally grateful for funding from various different agencies, without which this work that I'm going to present would not have been possible. Okay, so we make building blocks, and the idea of making nanoscale building blocks is to harness the novel properties that you can get by quantum confinement or dimensional confinement. All right, and I will talk broadly speaking, 3 or 4 different kinds of examples which are relevant to making devices or nano devices, no matter what the computational paradigm is. And first I will talk about how we can actually organize carbon nanotubes, which could be used as a single electron transistor if you want to, or you could use them as interconnects between devices which are nanoscopic in dimensions. And I'll talk about how we can organize them in various different configurations on a planar surface. And I'll also talk about certain scaling issues involved in obtaining architectures that would be useful for making devices. I mean, it's all very nice if, by making a single electron transistor, one of those, it takes a great effort to do that. But in order to use that for computing, you need to be able to make maybe a zillion, a million of those, or billion of those on a chip. And how do we do this? Or can we do it? Those are the kind of questions that I'm going to answer. I'm going to ask and answer some of those, and also highlight some of the challenges involved in various different material systems. And I will talk also about how we can use carbon nanotubes or other one-dimensional nanostructures, wired-like nanostructures, and use them as architectures wherein you can decorate them with other nanostructures like nanoparticles, amino acids, or proteins, which can change bond, chemically, or which can be addressed by light and other means as a means of creating device elements used for computation. And then I will talk about a couple of examples wherein we can make nanoparticles, where here you can see that the shape is nearly spherical, and how we can use them as building blocks to make 2-dimensional assemblies or arrays of or thin films of these nanostructures, or even chains of these nanostructures, and use them to create architectures that you may want to explore certain kinds of computing paradigms. I'll also show you some pretty pictures of how we can, really do origami at the nanoscale to be able to, get branched nanostructures of various different shapes that you can control in a predetermined way. Finally, I will show you a very remarkable example of how we can use self-assembled molecular layers to actually isolate disparate materials, which is going to be very critical, because if you're going to make nano devices, of course you're going to probably have insulators, metals, semiconductors, and all those, and you want to make sure that they don't mix together, okay, because they need to be stable. So isolating while maintaining the structural integrity of these structures is very important, and I'll talk about that a little bit before I conclude my talk. Okay, let's talk about carbon nanotubes. I mean, let's just say that these are one-dimensional structures or wire-like or molecular structures which have very nice electrical properties. Okay, and you can have ballistic electron transport, and depending upon the actual crystal structure or the chirality of the tubes, they can be semiconducting or metallic, and you can think about various different kinds of quantum devices you can make. As I said, if I want to make a real chip, I need to be able to assemble not one nanotube, but more like maybe 10 million or a billion nanotubes on a planar surface, and should be able to do this in a repeatable and a manufacturable fashion. So in order to do that, what are the key things that one needs to do? Well, I need to be able to control where the nanotubes nucleate, in which directions they grow, if you can make welds and junctions, and all this without compromising the quantum properties or the electronic and mechanical properties of the carbon nanotubes. Now, the good news is actually we can achieve almost all of these features. The bad news is not yet at single carbon nanotube level, because there are some serious physical scaling issues involved. Okay, and I'll mention those in a few minutes. So here we resort to chemistry, and where nature does most of the work, and we just have to get lucky by trying the right kind of things. And we use a precursor where we have a carbon source and a catalyst which is delivered from the gas phase. And the ion actually selectively, this catalyst selectively interacts with silica, SiO2, and in exclusion to silicon, and produces growth of carbon nanotubes only on silica. And there are two very remarkable things that happen for this particular chemistry. This is a scanning electron micrograph. The white regions are the regions where carbon nanotubes have grown selectively on silica. The black regions are silicon, where there is no growth at all. Okay, and that is the first feature. So growth on silica, no growth on silicon. And wherever you have the carbon nanotube growth, the nanotubes grow vertically. Okay, it's normal to the surface of the silica. So these are the two remarkable features, and you'll know why in just a moment. So this is just to, if you put this with your eye, you put a piece of silicon, nothing happens into the CVD chamber. If you put a piece of silica, then it blackens. Okay, so using just these two features, what I can do is I can use lithography, and I can make discs of silica on silicon, and I can grow, and I would expect to get structures like this, and indeed I get these wonderful pillar-like structures, which actually consists of clusters of carbon nanotubes. So this is pretty good. That means we can assemble bundles of carbon nanotubes. Good first step. And these are all unidirectional structures. These can be actually done by other methods also. For example, put down a catalyst, pattern it, and then do the growth. But here the beauty is catalyst. You just put the silica discs, and catalysts and the precursor, everything comes from the gas phase. So all the design comes before the actual growth occurs. So it's very powerful. Now you can also make these inverse structures by just inverting lithography. You can see you can make these porous structures, which could be used for plasmonics if you want. And you can actually control the sizes of these pores, and you can the shapes and so forth. And also can be used for a variety of applications in biology or membrane separation and so forth. The true power of this particular method of growth is that suppose I provide enough surface area on the side as well. Now I can actually get two-dimensional growth. Okay, and actually by extension I can get multidirectional growth by just chiseling the silica surfaces. Because the carbon nanotubes inherit the topography of the silica. All right, and if you had noticed earlier, you see there was no growth laterally, and that's actually quite an important point which I'll touch upon later. Okay, so here I'm just providing a solution, so I provide more surface area and I'll get growth like this. So these are cartoons. Let me show you some real example, and these are unprecedented, and these have not been repeated by any other technique. Of course, we can repeat it by using this technique. I mean, what we've done is, so you have silica, it has enough surface area here and here. You have carbon nanotubes growing in two different directions all at once in a single process. Okay, so that is a very good step. Additionally, suppose I chisel the silica at an oblique angle, I can get oblique structures. I can do, I can get all possible in-plane orientations if I do this in a circle, and the possibilities are endless. And the beauty about this is it's completely scalable. You can do this on a 12-inch wafer if you want. And you can see that over here, the dimensions are in hundreds of microns. So you can see that nanotubes have grown very beautifully throughout the wafer. We have done it for about 2 inches. That's the size of the furnace. But this is very scalable and manufacturable. And as I said, now I can make all different kinds of shapes of silica to get complex architectures. I can make MEMS structures. I can make microfluidic structures, and also very pretty structures like this, which may not be useful for anything much other than aesthetics. All right. In addition to doing all this, we can also, to make devices, you need to be able to also suppress growth where you don't want it. Okay, and we have a few methods of doing that. One is basically cover up the silica surfaces with a non-catalytic material, and by playing tricks with shadowing tricks, essentially you can restrict the growth to just 3 phases or 2 phases or just 1 phase. Okay, and the idea is basically the gold in this particular case covers the rest of the areas, and you get no growth. Additionally, you can also notice that by putting different amounts of gold on different faces, you can also control the length. Because in a device structure, obviously you don't make devices with all the same length of the elements. You need different elements with precise control. Okay, there is another very interesting way in which you can control the lengths of carbon nanotubes, and that is very non-intuitive. I'm going to very briefly touch upon this. You can see that this is the length of the carbon nanotube, and this is the silica thickness. So the thickness of the silica under layer actually plays an important role. So below a critical thickness, you actually get no growth, which is not surprising because that's, we do get selectivity, and that's what this shows. But actually, if you want to, let's say, get 2 different lengths of carbon nanotubes, all that you need to do is you can also just use 2 different silica layers with different thicknesses. I won't go into details about why this happens. But if you're interested, you can ask me during the Q&A session. Okay, so I said that, well, if you had looked at the pictures, these are all in microns. Bundles are microns, all right? But the carbon nanotubes themselves are nanostructures, all right? And ultimately, we are interested in making devices with individual nanotubes, in various different organizations. So I showed you earlier that you didn't have any growth laterally when you had, very thin disks. And so we wanted to explore why. So what we did was we took a bunch of silica particles of different sizes to see if there is a substrate size dependence in terms of getting the carbon nanotube growth, and we find that indeed there is. Here you can see that the growth, the carbon nanotube bundles actually grow on the particles of silica, and also, in fact, inherit the shape of the assembly of the silica particles. You can get walls of the carbon nanotubes, or you can get also 2-dimensional assemblies like this without any problem. In cases where you have isolated particles, you actually get, the carbon nanotubes growing, they fall down as opposed to being reinforced together. It's like, soldiers all standing close together and reinforcing each other. Even if you have weak one in between, you wouldn't be able to tell, he or she would be basically held together by the neighbors, by van der Waals interactions, actually. Okay, but what happens is when you decrease the size of the silica particles, what happens is these carbon nanotubes, they are not reinforced by each other anymore, and they behave like polymeric structures. That's because, as you decrease the particle size, see, the nanotubes tend to grow with a greater angular separation, and hence they do not have the scope to reinforce each other and get directionality. So entropy takes over, as opposed to enthalpy, and if thermodynamically speaking, and hence these curl up, and the nucleation also decreases as you decrease the size of the particles further, and all that you get is amorphous carbon. But and that is actually captured in this particular picture nicely. This is the Raman intensity of the D and G band. D represents disordered carbon, G represents graphitic carbon, which comprises carbon nanotubes. And this, as you decrease silica sphere diameter, you can see that the disordered part really shoots up, okay, and you don't get carbon nanotubes anymore. So this is actually a serious scaling issue. I mean, if I want to align nanotubes, at least by this method, okay, and in the configurations that I want, it's still a very, very open question. I mean, we can make very nice nanotubes and also align structures, but not of single elements as yet. Other good news, of course, is that we can actually grow these structures on almost any oxide. I showed you on silica, but we can do this on hafnia, I can do this on indium tin oxide, I can do on a variety of different oxides, because, I mean, that's very useful for device applications. Let's say you want to access electrical and optical properties of such structures. Let me show you a couple of results on some of the interesting electrical properties of these bundles. Suppose I have bundles like this, and I have like two terminals. What happens is initially, at low voltages, I get ohmic behavior. This is the differential conductance, and this is actually the current versus voltage plot. So it's ohmic for low voltages, but at high voltages, actually you get superlinear behavior, or you have more current actually flowing through than Ohm's law would allow. And the reason for this, we have figured out by a variety of different experiments and also density functional theory calculations, that the conductivity in this particular case is thermally activated, and that is not surprising. These carbon nanotubes are semi-metallic, and the interesting thing though is, when you increase the electric field across the terminals, the activation energy actually decreases, all right? So that's shown over here. Activation energy is decreasing as a function of the electric field in a Poole-Frenkel kind of behavior. What that amounts to is there are additional channels of or additional pathways for the carriers to go through the carbon nanotubes. Okay, and these could be used for for interconnects much more efficiently than, for example, nanotube with just one shell as opposed to multiple shells. Okay, I want to switch gears and talk a little bit about how we can make hybrid structures using carbon nanotubes. Okay, and we can put quantum dots on carbon nanotubes and use the coupling to think about making new kinds of devices and to explore new kinds of computing paradigms. One of the things is carbon nanotubes are very, very stable. They're very happy structures, very strong bonding. Now, in order to interface those with other materials, hence, is difficult. So the typical strategy that is undertaken is take this, beat the hell out of it in an acid, and then hope that bonds are broken, then attach other things to it. It works, as you can see here, gold nanoparticles decorating the carbon nanotubes, but you have no control over where this happens. So in order to make a device, you want to be able to do things precisely. So we explored a few different approaches. One of them is by using kilo-electron-volt ions. You use them to actually break bonds, okay, and use this. You don't not only get spatial resolution by controlling the size of the ion beam, but also you can do this in a controllable fashion in terms of how much damage you create as opposed to destroying the tube, which can happen when you put it in an acid. And after that, you can use mild chemical treatments to then attach this with molecules or other structures. So just as an example, you can create structures like this, where you have a carbon nanotube like this, and you have this nanoparticle or a protein, which is electroactive. I'll show you one example where this attaches onto this, and you can now manipulate the IV characteristics of the carbon nanotubes by perturbing this. So you can use this as a switch, perhaps. Okay, and I'm sure you'd probably be able to think about other kinds of ways in which you can use this for computing. But this is the basic idea over here. And here, for example, this could be a biological analyte. This could be a chip that could recognize certain biological molecules when you have an analyte because of its interactions with these various different elements, which are different proteins, for example. Okay, so now you have, I'm breaking bonds with ions, okay, and then I'm exposing it to air. This is just one simple example. You can see this is actually the infrared spectrum. When I have irradiation, I can see all these carboxyl groups, allyl groups, and other moieties that show up, but when I have pristine nanotubes, nothing much happens. So by what this says is, only in places where I hit them with ions, I'm able to functionalize. So I get site selectivity along the segments of the carbon nanotubes. And this is Raman spectra, which shows that the D band increases, which means that I'm actually indeed creating defects. So no surprises here, but this is actually the first time demonstration of selective functionalization of segments of carbon nanotubes. Okay, and we can do various different kinds of chemistries here. For example, use the carboxyl group and attach gold nanoparticles, and you can see that only the irradiated regions have the gold nanoparticles and others don't. All right, we can do this for fluorescent nanospheres or microspheres, and you can do this for various different materials, and you can see that the length scales are very well controlled, and also you can control the shapes of the, or the location where the nanoparticles basically attach. Now let me show you an example which could be relevant to biocomputing, or I don't know, or it could be biosensing, depending upon how you implement it. Suppose I use an electroactive protein. Okay, this is actually azurin. It has a very high dipole moment, and in this particular case, we attach this by electrostatic interactions to certain segments of carbon nanotubes. And I'll show you that when we did Raman spectroscopy, what we found was that pristine azurin shows this particular signature with certain kind of coordination, or basically certain kind of shape. Okay, so and which you can relate that to a certain kind of dipole moment. Now, if I have that attached to carbon nanotubes, you see a different signature. Okay, and what that means is its structure is distorted, and hence its dipole moment is also distorted. Okay, now the IV characteristics of the carbon nanotubes should be modified, or should be distinguishable in these two cases. The additional thing is, suppose I have this kind of configuration, and I use an external stimulus, maybe some kind of biological molecule that interacts with azurin, then I can actually modulate the characteristics over here, which can be used for some kind of recognition, computing. I don't know if it can be used for more than binary, but definitely it can be used for binary kind of operations. Now, just to show you that this indeed you can do this, you can see that the azurin derivatized nanotubes show the IV characteristics that are like this. Functionalized tubes show these, and suppose I expose them to thermal stresses, then the hybrids actually show irreversible behavior, while the functionalized tubes show a reversible behavior. So, I can see that the changes in the conductance actually are quite large. Okay, so you can use these as different states if you can design architectures appropriately. Okay, I told you that we wanted to do modify nanotubes in a mild way rather than in a very haphazard or in a very aggressive way. But we need to be careful, and just wanted to show about what ion beams can do. You can see that they can cut the nanotubes, or they can thin them, or do nothing to them, depending upon what the diameter is. In addition, you can also weld them. Here are two proximal nanotubes, and you can see that they are welded over here. All right, and you have multiple welds over here. So it can be also, your ion beams can also be used as a tool to create networks, okay, of these nanostructures. And that would be useful for creating architectures. Okay, what does it do to the electrical properties when I just hit nanotubes with ions? You can see that here this is actually a transmission electron micrograph showing the basal planes of graphite, or of the graphene sheets that are folded of the nanotubes. When I bombard them with ions, you can see that there is defect creation and reconstruction. The shapes are changing. This is the atomic scale structure. And in this particular case, when we have very high doses, it is not a tube anymore. You can see the hollow in all these cases, but in this case, there's no hollow. And so it actually becomes a nanorod. So what happens to the electrical properties? Well, you can see over here that when I have, before radiation, the resistance versus temperature behavior has this activation energy of around 200 millielectron volts, semi-metallic basically. But after irradiation, it changes a little bit. But the thing is, you can controllably do this, okay, as opposed to destroying the nanotube, which we do when you use acid treatments. There are other simpler ways of doing the same kind of things that I showed you here. For example, if I put networks of nanotubes, if I put a mat of nanotubes and this way, and I want to create welds, I could just do that by passing high currents. And this movie actually shows you a very preliminary experiment wherein actually you see some sparks. So now that you've seen the sparks, let me tell you what's going on really. You just spread out some carbon nanotubes, with 4 terminals and pass current. And this arcing occurs because of, basically carriers jumping across the overlapping nanotubes. And if you look at the changes that are happening, the changes are very similar to what I showed you in ion bombardment case. You get cutting and thinning of carbon nanotubes. You get also cladding or welding of tubes and so forth. And this you can do it, of course, in a very cheap way. And the very interesting thing here, though, is once you have these mats of nanotubes and you're actually passing high currents and you're creating sparks and you're breaking nanotubes and so forth, you would expect that the conductance will actually go down. Correct? But what happens initially is the conductance goes up in short time frames. And the reason for that is, even as you're creating defects, you're also creating more number of pathways for the current to be carried through in this network. Okay, let me show you a different strategy of derivatizing nanotubes with other kind of quantum structures. I'll show you 2 examples. And here the emphasis is on creating large quantities of these hybrid structures as opposed to organizing them. And the approach that we took was use microwaves, all right? And here we take nanotubes, and we also take metal ions and just microwave it. And by reducing the metal ions, we get either metallic nanoparticles or semiconducting nanoparticles, depending on what chemistry you use. And you also functionalize the tubes because of interaction with the microwave and the water and the carbon nanotubes. You can see over here, you're creating defects, all right. The D band goes up, so defects are created. And in addition, you're seeing that the CC, the allyl bonds and carboxyl bonds are evolving as you increase the microwave exposure. The beauty is that all this happens in a minute or 2. Okay, you just take nanotubes, you put the metal salt solution, put it in a microwave, simple microwave, turn it on. This is what happens. If you were to do this otherwise, by conventional routes, it'll take you about a day to do this, and also you'll be destroying the tubes and their properties. So this is actually a very neat and nifty way of manufacturing these hybrid structures, which can be used as building blocks again for various different architectures. Here is another example. Just by varying the chemistry, we can do copper oxide or cadmium sulfide or any of the semiconductor quantum dots, and with controllable shapes on these other skeletons or skeletal networks of carbon nanotubes. So, there are various different routes in which you can actually create this kind of hybrid structures and also organize them by using these one-dimensional structures. I want to shift gears again at this point to talk a little bit about storage. That is, information storage, because I did hear there are, in quantum computing, you can have different kinds of paradigms where you use storage heavy algorithms and otherwise. That's the extent that I understood. But here, the idea, our motivation for doing this was to create high density data storage, okay, where you use each nanoparticle as a bit, okay. So this is actually a very pretty picture. You can see that these are nanoparticles of iron platinum, okay, which are supposed to be magnetic, but in this particular case they are not. Well, or they're magnetic, all right, but they have very low coercivity, okay. And ideally for this to store data, what you would need is high coercivity, so that the spin stays put the where you write it. So you'd like a combination of this and this. But what was shown is, when you make these nanoparticles, because of the size, these are superparamagnetic, which means that the spins are actually, they fluctuate because of the phase of the nanoparticles. So in order to get the high coercivity phase, you need to anneal them, you need to heat them up. Once you heat them up, you get high coercivity, all right, but you're destroying the nanostructures. So the challenge, one of the challenges here is to make really small particles that have high coercivity, that can hold the spin and retain the shape too. And they need to be stable to thermal, chemical, and all other kinds of stimuli. So we took a couple of approaches, one not very successful and one extremely successful. I want to just share with you both of those. I won't bother with you with the details in the chemistry here. Just want to say that we take platinum and iron and we just put this additional element, antimony. The idea was to get the ordering or get the crystal structure that gives the high coercivity phase at a lower temperature, so that we don't go to high temperatures which would destroy the architecture. So when I plot the coercivity as a function of annealing temperature, let's look at the green cartoon that I've drawn over here. You need to go to about 500 degrees centigrade in order to get the high coercivity phase. Okay, by the time you're destroying your assembly, so it's useless. Now, by adding this antimony, the idea is antimony is a big atom, so and it also doesn't like to stay in the lattice of iron and platinum, so it likes to go out. The moment you heat that a little bit, it's going to shuffle the other atoms, and hopefully that will drive it to the high coercivity phase. That is the idea, and indeed it does. As you can see, at about 250 degrees centigrade, you start to get the high coercivity values. But the problem is that since you're increasing the mobility, let's look at just this graph over here. The particles also start to coarsen. Okay, so we end up with the same problem. So we said, okay, let's take a completely different approach. Let's try to solve many problems at once. We became more ambitious actually after failure. And in fact, as you will see, this is quite a remarkable, approach that I'm going to talk about. What we do is we take, we use droplets of water. Okay, nano droplets of water. These are microemulsions for those of you who know chemistry. Basically, we reduce iron and platinum in this confined environment, make the nanoparticle iron and platinum. Okay, these are still super paramagnetic, so these are not high coercivity. But the one additional thing that we do is we coat it with a very thin shell of silica, so that if I want, I can heat this composite up and I'll be able to change the crystal structure inside, but I want to, I will still be able to preserve the overall shape of the particle. Okay, that is the overall idea. And additionally, I can also functionalize the surface with the molecules and hence, disperse it in other matrices and biological systems, or help it to assemble and get these kinds of structures. This is a cartoon, of course, and this is actually realized, and I'll show you the various aspects of it in the next few minutes. You can see we can control the particle size very beautifully, and none of this is optimized here. We can optimize it and get really great pictures, but the point over here is that you can control the particle size, and just by adjusting the water droplet size by simple microemulsion chemistry. And once you have this thin silica shell, in the as prepared form, it looks like this. And once you anneal it, you see that it's still, they don't coalesce. They're not agglomerated. I mean, they're kind of sticking to each other, and I'll tell you why in a moment. But the point is, there's no change in the particle size. That's quite important. So we have solved the problem of, change in the shape. That's good. But the assembly still looks very bad. And the reason for that is because silica, you have this OH group sticking out, and those tend to form hydrogen bonds. So you need to functionalize the surface. So we put in a molecule, and once you put the molecule, you can see get a much better assembly. And once you heat it up, you actually destroy the assembly. But I mean, you can reassemble them, of course, and by redispersing and so forth. The beauty here is you have, for the first time, after annealing, nanoparticles that are high coercivity and in the nanoparticle shape, where the assembly is not, where the shape is not destroyed. And that is seen over here. You can see that you get the high coercivity shown by the blue coercivity curve, and the red one, there is, which is the as prepared case, it's super paramagnetic. Okay, we can use these building blocks to also, string them together into nano chains. If these could be useful for some kind of, you can use these to make, let's say, like complex structures, like of different shapes to explore different architectures. The idea here is quite simple. We can make particles, and we use two different kinds of molecular braiding agents, where we can actually make chains not only of controllable length, we can control them very precisely, but also of controllable diameters. All right, and this is just to show that we can do this for various different materials, and and this we have explored mostly magnetic materials, and this could be something that could be useful for dilute magnets, for various spintronic applications. Okay, one of the big challenges in nanocomputing device architectures, of course, is heat dissipation. Okay, and what I hear from the experts who do this for a living is that even if you make, let's say, if I were to make carbon nanotube device right now, okay, we somehow overcome all the scaling issues and figure out how to separate the different tubes and so forth, and make a device, most likely it will just blow up. Okay, just because of the amount of heat that is dissipated. So we need to really think about ways in which you can get out heat, and this has to be new ways, obviously, because things are happening at the nanoscale, and it's very poorly understood. One of the strategies that we have taken is to work with materials, work with thermoelectric materials, wherein you can actually use, you can integrate that with interconnects and other switches, so that you can use local refrigeration to cool hot spots and remove heat away. I'll just show you a couple of examples wherein we are looking at bismuth telluride, and here basically just wanted to show that we can make nanostructures of bismuth telluride, I mean single crystals, without using any kind of templates, physical templates really. And the idea here is, of course, since like thermoelectrics, you want to basically get high electrical conductivity and you want to get low thermal conductivity, right? And the electrical conductivity you want to tune by using quantum confinement, so getting more states near the Fermi level, but getting low thermal conductivity you want to actually obtain by the size confinement because of the phonon scattering from the surfaces and the boundaries of the structure itself. So the nanostructures that we've made actually give you, well, the films of nanostructures at least, give us actually very promising Seebeck coefficients and also electrical conductivities, which we are hoping we can, when integrated with the interconnect structures, which in nanocomputer, in conventional nanoelectronic devices, this could be a way in which you can dissipate heat. Okay, we can make complex architectures of these as well. So these are not unlike what I showed you in the case of carbon nanotubes, but the methods used are completely different. You can see that I can control the degree of branching, and everything here is a single crystal. Okay, and these are all modulated by actually using molecular templating agents. And this kind of control would be very useful to make like architectures where, let us say, I want to, let's say this is a hot spot, I want to carry heat away from to various different directions. I can actually design, you can think about designing these kind of thermal conduits. I'm going to skip the mechanism part of it because that's probably going to be not too relevant. The last example that I want to give actually is, I think, would be relevant for any kind of nano device, irrespective of what the computing paradigm would be, and that is in order to isolate different materials. Okay? And of course, structural integrity needs to be preserved no matter what. It can't crumble. So I'm going to take the simple example in the current microelectronics device paradigm and also the nano paradigm, wherein copper integration with low dielectric constant materials is a problem because copper diffuses very quickly into the adjacent layer, and also it doesn't stick very well. Okay, how can we actually solve this problem, and do this by using minimum amount of material? This will cease to be a nano device if I need to put a micro layer in between, to isolate it, or even let's say this dimension is of the order of, let's say, 45 nanometers, and the diffusion barrier layer that I need to put in, if it is going to be 10 nanometers, that is a large amount. So I'm compromising the area that I need for low resistivity copper. So ideally, I'd like to have this as as thin as possible. The diffusion barrier should be as thin as possible to isolate as well as provide integrity. So we tried a completely wild idea. This is an undergraduate project actually of 5 years ago, and the amazing thing is it worked. And of course, we have been exploring this various aspects of this for the last several years. The idea is, instead of taking a brute force approach, which actually works quite well for micro scale, but doesn't work well for nanoscale. Here you put tantalum or tantalum nitride or some other material where the interaction is minimized to some, like some smaller length scale, and these two stay separate and everything is fine. But as I said, that you need a critical thickness of this for this to work. So we said, let's take molecules with certain groups on top, certain groups on the bottom, and these are going to be CC bonds essentially, which are very happy. And this is going to create a vacuum-like potential between these two materials. So it's going to be harder for this material to jump across, okay, these atoms to jump across, because it's being bonded chemically, locally here, immobilized, and same thing is happening over here. And these molecular layers can be made very easily. It's like, basically dip coating. It's like molecular beaker epitaxy, and it's really a graduate student's dream. I mean, you can take these molecules in a solution or a vapor phase, and they assemble like soldiers here, again driven by thermodynamics, and because of van der Waals interactions between the molecules, and you can synthesize the molecules with whichever terminal groups that you want. Okay, let me show you how it works. So we actually make metal oxide semiconductor structures to study the diffusion or study the transport of copper across. So when we have no molecular layer in between, you can see that the leakage current actually goes up rather quickly, and this corresponds to the breakdown of the SiO2, and this happens at rather low times. But once I put a single molecular layer, and the thickness we are talking about the molecular layer is 1 nanometer, 2 nanometers max. Okay, you can see that the failure is postponed, and also the leakage currents are much smaller. And to give you a perspective on like how good are these compared to the barriers that are used currently in devices, again leakage current as a function of time, you can see without any barrier, it's pretty bad. Okay, and if I have conventional barriers of similar thicknesses, like of these two molecular barriers, what happens is you can see if I have an amine terminated layer, I get improvement, and if I have a carboxyl terminated layer, I get really very large improvement. And in fact, it's better than conventional solutions of similar thicknesses, and this is without any optimization. Okay, so this is really a truly powerful way. And while of course there are a lot of other issues to be addressed for integration in a device, I think these kinds of new approaches need to be developed to be able to make new kinds of nano devices which take advantage of other things other than binary computing methods. I mentioned structural integrity, so I will just talk about that for the next few minutes before I wind up. Basically, things shouldn't break. Once you're making them, they shouldn't break, right? And how do you ensure this at the nanoscale? Okay, and this is a real challenge because you have so many different kinds of materials all close together, and you want the interaction to be very good or strong, but at the same time you don't want them to mix. Okay, and so we actually explored the effect of these single layers as glues to see if we can hold it also in addition to isolating them chemically. So we also have a technique which is actually very powerful to measure the interfacial adhesion or toughness quantitatively. And the way we do this is we create a test structure like this. It's a 4-point bending test structure, and we create a notch. And once you bend it, from the notch tip, you have a crack going through, and it'll grow lateral. It'll go down to the interface, the weakest interface, and grow laterally, which gives rise to a load versus displacement curve that looks something like this. And this plateau corresponds to the crack going through the weakest interface across. Okay, and from that you can actually get the toughness value quantitatively. In fact, very few places in the world have this machine. We built it ourselves. We didn't invent this technique, and Intel actually uses this as a benchmark. So you have load versus displacement for a copper silica interface without anything, and the value that you get, the toughness value that you get is 3 joules per meter squared. I'll tell you what this means in a minute. Once I put a molecular layer with a sulfur group on top, and a propyl group in between, you get 9 joules per meter squared. Again, unoptimized, and have triple the toughness value. Okay, And to tell you what these numbers mean, in an Intel chip, I don't know, in a Pentium chip, maybe it is, I don't know what the latest chip is called, but typically it is, for an interface to be considered stable in the chip, the value that you need to meet is about 5 joules per meter squared. So without optimizing and using a single layer, okay, and we have actually tripled the value, right? So that is not all. And we know why this is happening. I won't go into the gory details of the spectroscopy studies that we did, but let me just mention that copper and sulfur bond. Okay, and that bond is actually shown by spectroscopic signatures over here, and the breakage actually occurs on the silica side of the interface. Now, we wanted to study the thermal stability of these structures, because in manufacturing, that's quite important, because these molecules would probably get fried. That's what our thought was. But remarkably, what we found was, by heating up, we were actually enhancing the adhesion. And let's look at that. The interface toughness, plotted as a function of the annealing temperature. So I showed you this data point earlier, so you get the threefold increase. But as we heat it to, let's say, 100 or 300 degrees centigrade, it actually degrades, the toughness degrades. And above 300, however, it starts to increase again. And above 500, in fact, this interface is not the weakest interface anymore. Okay, failure occurs in the epoxy. So what we're getting here is actually colossal toughening. All right? So what's going on? I mean, this is totally counterintuitive, because these molecules, are organic molecules, and normally people study these on surfaces, and these desorb, and about 300, they're not even considered for any use. But this suggests that we can use these at high enough temperatures if we can use them at interfaces as opposed to surfaces. And let me just tell you what's happening, and I'll just show you the modeling calculation and spare you the experimental part. At low temperatures, when you anneal it, see, this part of the bond actually stays stable, and this part, however, actually is unstable. The OH groups that you have on with the silicon actually tend to form SiO-Si bonds, but they revert upon cooling. Okay, so the bonds formed here actually are reversible for less than 400 degrees centigrade. So this remains a weak link. Okay. And over here, though, at higher temperatures, the bonds that are formed stay put, and they are stable, and they do not revert to the SiOH bonds, and hence you have a case where both the interfaces are actually strengthened remarkably. So what does that do? Well, we actually did some theoretical calculations wherein you take a single molecule and stretch it, and what you find is the energy required to break the stretch and break the molecule, in the case of where you have just a hydrogen bond, is shown over here. And once I add a SiO-Si bond, then actually you're nearly doubling, increasing by a factor of 2.5. And that actually corresponds very well to the experimental measurement that I showed you. Well, I hope I have touched upon a few of the topics that are relevant to realizing nanoelectronics devices, okay, wherein you use nanostructures where quantum confinement effects predominate, right? I have ignored a complete field here in my talk, where people grow these semiconductor nanostructures, quantum dots, by MBE and other means. And this one, of course, is an alternative approach, and perhaps much more rewarding, much more, I would say it has much higher potential rewards if you can do this, because you can make these structures, you can tailor them at the atomic scale, and then you can actually also assemble them by using bottom-up strategies, by harnessing chemistry and nature, and of course perturbing it with top-down approaches. So thank you very much for your attention, and I'd be very happy to answer any questions that you may have.
The experiment on the nanotube properties changing by ion irradiation was very interesting. May I know, how does these properties change? Is it dependent on the fluence of ion, or the charge on the ion, or the nature of the ion? You've chosen gallium or some other.
Okay. The answer to the question is all those, actually. I didn't go into details, but we have discussed this in the papers. Fluence is important. Actually, the combination of fluence and energy is very important. Okay. And generally, the higher the energy, the lower the, well, in the energy range that we have looked at, the higher the energy, the lower the fluence that the nanotube can take. The diameter of the nanotube is important. Of course, the species that you use is very important, you know, argon versus gallium, just because of the different masses and different cross sections of interactions when you're hitting the carbon atoms.
You've touched KeV ranges,
yes,
and we can go to MEVs and.
You could, but you know, if you go to MEVs, I think the interactions would be much smaller because of you know, the cross sections actually rapidly fall off. I think the most attractive range is perhaps just a few keV. There have been a lot of computer simulations for the lower ranges for a few hundred eV, and also recently for keVs. And you know, there are a lot of things that you can do in that range to modify controllably.
Thank you.
You mentioned the interaction of proteins with carbon nanotubes. I just wanted to know the primary motivation for that. And have you studied optical properties of CNTs?
Have I studied what?
Optical properties.
Of the nanotubes?
Yes.
Okay, I haven't studied the optical properties of nanotubes. That is easy. Now the proteins, motivation others have done the protein carbon nanotube hybrids also. But there it was non-specific or not site selective. We wanted to look at, our idea was, if you want to make a device, okay, and our idea of a device is to have multiple elements, okay, like a chip, as opposed to a single nanotube device. And in order to manufacture that, how do you do that? You need to be able to, you know, precisely position different kinds of proteins at different places. How would you do that? So we wanted to look at nanoparticles and biological systems for, you know, obviously different applications. And the protein that we looked at obviously was thought of, we thought of it for computing, okay, bio-inspired computing or switching, whatever you call it, and also for sensing and recognition.
Actually, I'm a biologist, and you are using biological molecules in this making the chips. I have a very small apprehension about that. You are taking sulfur and proteins and all this. Many of the microbes develop in it. I don't know, in your experimental design, you take care of the microbe growing on these surfaces in natural conditions.
In our case, no, we didn't take care of it. In fact, this is our forays into using the proteins you know, as hybrid structures with carbon nanotubes was just restricted to that, to making it and exploring to see if there is any responses that we can get because of the dipole moments. So if there is any effects of, you know, microbes and so forth, it is not evident, at least from our experiment, but I'm sure that will be evident, you know, that will be an important factor to consider.
Said that after annealing and before annealing, there is change in coercivity. And if you are doing the annealing at say 500 or 400 degrees Celsius, I think, what should be the medium at the time of annealing? Whether it is in open atmosphere or in argon atmosphere or it should be in inert atmosphere. Okay. There is chances that since the carbon nanotubes are very you can say in a naked position, the carbon atom. So there may be chances of oxidation or not, okay, or they are very.
Okay. In the case of iron platinum,
yes.
The question
what's the environment
right,
at the time of annealing at this temperature?
Right. We have done it in various different environments, and the ones that I showed you are in inert environments. These are in vacuum or in argon, and of course the environment matters. I didn't emphasize that, but of course we do this. You can do this in air too, but you would have oxidation issues.
Okay. Ram, I had a question for you. Could you care to comment on the status of predictive tools that will tell you how these different nanotubes, for example, might grow in certain configurations? Because the next step before you get into devices, and in order to design those devices, you need to have a certain level of predictive capability to say how would you control the the temperatures and so on and so forth to grow the right device?
Actually, that's an excellent question. And in fact, this is an area, I was thinking about this last night when I was going through my talk for carbon nanotubes. You know, carbon nanotubes are 16 years old now, since their discovery, at least since their formal discovery. And nobody really knows how they grow and why they grow. And there's a lot of guesses. Of course, there is some correlation in terms of what kind of materials catalyze them. There are theories about the structural inheritance of the carbon the graphene shell from certain planar facets of certain catalysts. And also, it's very interesting that almost all catalysts for carbon nanotube growth are magnetic. Okay, so in this perhaps an area where this soft computing tools can be used to at least open up areas or where which can be further explored experimentally. I think the opportunity is really huge, and in fact the timing for that is perhaps good right now, because the excitement in carbon nanotubes and particularly nanotubes and of course other fields has been make new things and see what's going on, and it's been produced a lot of excitement. And now I think the time is ripe to really understand and comprehend and reflect upon how it's happening to really get control. And without getting that kind of control, I think, at least I believe, that that control is critical to be able to go to the stage of making a device in manufacturing.
Absolutely. Thank you very much.
Thanks.
There's one other comment.